Alrighty then, moving towards a more realistic universe. Let's start with our old familiar Margulis front that we had seen, where we did the cylinder collapse experiment in the lab. Remember the saline water in the middle, warmer fresh water in the outside. Rotation, pull out the can and see what cone is created. That interface separated densities rho 2 and rho 1 with an angle gamma, and we had used this two paths to balance pressures and derive our geostrophic currents in terms of dp dy and dp dx, and we derived the Margulis relation for the flows parallel to the interface on either side. The shear, if you will, u2 minus u1 was derived as g prime, our reduced gravity, tan gamma, the angle of the front, divided by 2 omega, because we are in a tank. Rotation and gravity are in the same direction, so this was our simple expression, where g prime of course is g delta rho over rho 1. Delta rho of course is the difference in the densities. So you can see how the concepts are now adding up. We are going from large scale balances towards the energy that is locked up in these large-scale balanced flows we have been looking at in terms of their temperature distribution, wind distribution, and now saying what potential energy is locked up in those structures we have been looking at. So let's say for simplicity we'll assume the lower layer is at rest, so U1 is 0, and just simplification to show the concept of the ratio of APE and KE, available potential energy to kinetic energy, so that when we release some of the available potential energy, what can we expect in terms of the kinetic energy? That's all. Okay, so U2 equals G prime. We approximate tan gamma with gamma for small enough angle, divided by 2 omega, so the lower layer at rest. KE in this context, going back to our tank, go from H to H. H is again the interface, in which case it's you are going from within the cone to outside the cone, so H to H minus L to L. The horizontal extent of the tank is 1/2 rho 2 U2 squared dy dz. Very simple expression. This approximates, this turns out to be 1/2 times rho 2 times g prime gamma squared over 2 omega squared times h times L. So you can see already in your head we are going after the vertical scale of motion versus horizontal scale of motion. As soon as we say horizontal scale of motion, we're going to bring in the constraint of the Rossby radius of deformation, right? So that's where we will head. So you can write obviously this ratio APE or KE as 2/3 L over L rho squared. What is L rho? Obviously it's our Rossby radius of deformation for the tank, expressed as NH over 2 omega. N is the buoyancy frequency. Okay, so in this case we're assuming rho 1 and rho 2 are basically fairly close to each other, heading almost to 1. Okay, for balanced flows in this sense, APE and KE, the ratio can be approximated by this relation here, 2/3 of L over L rho squared. L is essentially the scale of our horizontal flow, and L rho is the Rossby radius of deformation. Okay, that's our equation that looks simple. We can take this and go into the atmosphere and the ocean and actually see what are the scales we are looking at. So L is order 5,000 kilometers in let's say mid-latitudes. L rho is about 700 kilometers, as we had seen before. You plug in the numbers for G prime N H over whatever it was, or 2 omega. Okay, so L or L rho squared is about 50. What does it mean? That means the amount of potential energy locked up in these distributions of temperature and density is about 50 times the kinetic energy. Okay, so most of the even though we see very fast winds, we see all kinds of storms and so on and so forth, the large scale structure remains this way when you average over long enough time scales of a season or a year, which means the rotation is somehow taking the system and rearranging the structure that it's locking up the potential energy. Okay, so it's available potential energy converting to KE is in that sense much smaller. Actually, if you do these numbers for the ocean, L over L rho squared is 400. Because the ocean is heavier, if you create the tilts in the ocean, we'll see tilts differently. We'll look at this in the next chapter. So ocean has even more potential energy locked up in its mean structures because of rotation. So rotation can hold these kind of tilts. That's the main point of this figure. In this situation that we looked at before, if it is not rotating and you created an interface tilt somehow, when you let go, lighter fluid will go up, heavier fluid will come down, they will overshoot, and then there will be a few waves sloshing around and energy is lost to the friction, and then boom, you have a flat interface back to minimum potential energy. But let's say somehow we created a situation where the slope is constantly maintained and there is always a tendency to want to adjust to the minimum PE. How do you maintain this tilt? That's essentially what we are saying here, that with the radiant energy distribution in a rotating system, you can create an interface that is tilted, right? We have lighter fluid and heavier fluid, and you can maintain that. In this case, the adjustment doesn't just go in the vertical plane like this with horizontal distribution of KE and then back to minimum PE. The interface can be maintained, and the exchanges because of this release of available potential energy will happen as back and forth along this wedge here. Okay, so that's where the instability of the baroclinic eddies come in. We are kind of combining concepts now. We have already seen the cold front and the warm front, where the warm air was going poleward and upward. Cold air was coming equatorward and downward. Right? So this is what general circulation is all about. We have to get into the details of how actually the zonal flows, zonal asymmetries, and meridional transports are happening. Why do we mention eddies? Because we said the meridional circulation in the mean is very weak beyond the Hadley circulation. So the eddies were doing all the work of transporting energy and heat poleward. Okay? The only additional complication here is that conversion of APE into KE is not happening in this non-rotating sense of just a vertical collapse, but it's happening along these tilted surfaces. That's all you have to learn out of this. So release of available potential energy in baroclinic instability, whether the interface sloshes away or a circulation is set up depends on the heating and cooling. So here the interface will just slosh away because this interface was held and just released. There is no other mechanism to hold it up because it's either rotating very slowly as in the lab, or it's not rotating in this case. Okay, whereas here you have rotation that is strong enough, and you have distribution of radiation that can create this wedge of stability and hold it there. Okay, simple concept. Just get the physics, and note that the equations we are using are fairly simple. Okay, so just go through them, read the book, listen to the podcasts as many times as you want to make sure that you understand the concepts. Okay.